Hey gang, this last type of probability that I want to talk about with you is kind of a tricky one. It's conditional probability, sometimes known as Bayes probability-based theorem. So we're going to be looking at this in the context of a drug situation here, where you got an employer who wants to test their employees for drugs. So a large company is hiring to fill positions in its warehouse in an area where it is known that 15% of the applicants use drugs. Part of the application process involves drug screening. The test is not perfect. It returns a false positive 8% of the time. So that means a false positive is when somebody's not using drugs, but they test positive. And a false negative 12% of the time. So a false negative would mean somebody is using drugs and they test negative. Let U equal the event that applicant uses drugs, and P equal the event that the person tests positive. We won't worry about that part. So calculate the probability that a randomly chosen applicant doesn't use drugs, given that they test positive. So first, I'm going to show you one way of going about this, and that is to think of having 1 million applicants. And we could choose a smaller number. I just went with 1 million just to make sure we end up with whole numbers. So if we have 1 million applicants, that means 15% of the applicants use drugs. So 15% of 1 million would be 150,000. So we're saying that there are 150,000 drug users among these applicants. It says the test is not perfect. It returns a false positive 8% of the time and a false negative 12% of the time. So this also means that there are 850,000 people that are not using drugs. Okay, so false positive 8% of the time. That means 8% of these people who aren't using drugs are going to test positive. So we need to know what's 8% of 850,000. So 0.08 times 850,000, that means 68,000 people out of these 850,000 are going to test positive. 68,000 test positive. For the drug users, we've got 150,000 drug users, and there's a 12% false negative rate, which means 12% of them will test negative. But that also means that 88% will test positive. So if we take 88% of 150,000, we get 132,000. So we have 132,000 positive tests here. So that means we've got a total of 200,000 positive tests. Okay, so we've got 200,000 total positive tests. 132,000 come from the drug users. So 132,000 divided by 200,000 gives us 0.66. So we're saying that if you test positive, given that there's a positive drug test, the probability that the person is on drugs is only 66%, or 0.66. Now, a lot of people struggle with this because when they see that there's a false negative rate of 12%, that means that there's a true positive. That means that the test gets it right for the drug users 88% of the time. And so people think that that means that there's an 88% chance that you're using drugs if you test positive. When in reality, there's only a 66% chance. And that's because we also have these false positives. Okay? So these false positives contribute to positive testing, and therefore reduces the probability that somebody might be on drugs if they test positive. Okay, we're going to look at a COVID example in our homework this week. But this is a situation, especially with rare instances, things that happen rarely. A positive test result does not necessarily mean it's likely that the person is positive for whatever you're testing. Okay, let me show you what this would look like with a if we kind of use an area model. So there is an 85 or a 15% chance that the person is using drugs. So here we'll say drugs, no drugs. This is 0.15, this is 0.85. And then this is a positive test result and a negative test result. Okay. So for the drug users, there's a 12% false negative. So we would take 0.15 times 0.12. For the positive test results, then, it's going to be 0.15 times 0.88, because if 12% of them test negative, 88% will test positive. Down here, we can say that we have 85% that don't use drugs, but 8% of them, so times 0.08, will test positive. And that means that of the 85%, 92% of them will test negative. Okay, so we could fill all of this in. So let's do 0.15 times 0.88, and we get 0.132. 0.15 times 0.12 is 0.018. And you'll notice that those two numbers add up to 0.15 because that's the percent of people using drugs. Down here, 0.85 times 0.08. 0.85 times 0.08 is 0.068. And 0.85 times 0.92 is 0.782. Okay. So now we can see these are the different probabilities. Okay, there's a 13.2% chance that we get a drug user that tests positive, a 1.8% chance that we get a drug user that tests negative, a 6.8% chance we get somebody who's not on drugs that tests positive, and a 78.2% chance that we get somebody who's not on drugs and tests negative. So if we want to know, calculate the probability that a randomly chosen applicant doesn't use drugs, given that they test positive. So we're given this positive test result. Okay, so we would add up those totals. 0.132 plus 0.068 is 0.2. That's our total. We have 0.2 total positive test results. Of those, what's the probability that randomly chosen applicant doesn't use drugs? So actually I did the wrong thing over here. I did the probability that they do use drugs. The probability that they don't use drugs, 0.068. So 0.068 divided by 0.2 would come out to 0.34, or 34% chance. So there's a 66% chance that they do use drugs, a 34% chance that they do not use drugs. So that's the issue with false positives and false negatives in a drug test, is a positive test result doesn't always guarantee that someone is using drugs. Let's look at the other question here. Calculate the probability that a randomly chosen applicant uses drugs, given that they test negative. So now we're given this negative test result. So if we add up the 0.018 plus 0.782, we get 0.8. So we're saying 80% of applicants are going to get are going to return with a negative test result. Of those, 0.018 of them are using drugs. Okay, so 0.018 divided by 0.8 is 0.0225, or 2.25% chance. So there's a little over a 2% chance that if someone comes back with a negative test result, they're using drugs. Okay. There's also a 34% chance that someone who comes back with a positive test result is not using drugs. Okay. And this has ethical ramifications too. If you are testing for some disease and you come back with a positive test result, but there's a 34% chance that you don't actually have the disease, you may be doing a lot of worrying for nothing. And so what we really want to try to do is get this false positive rate down lower so that we can be more certain that if there is a positive test result, that the person is actually using drugs, or the person does actually have the disease. So we want to try to, again, get that positive test result down, or false positive test result down. Okay, so that is conditional probability.